Question 8 on the practice final says that we have two parallel plates hooked up with a potential V0 separating them, so that the charge positive Q is on the top half, charge negative Q is on the bottom half of essentially these two parallel plates, which is like a capacitor, and we have this battery hooked up so that we have this potential, and then we disconnect the battery. So this is similar to one of the worksheets that we did in class, where we have, again, our parallel plates hooked up with the battery, we remove the battery, and we want to see what happens when we slide a dielectric into the space between these two parallel plates. It's a linear dielectric, and we want to explain what happens to terms like the electric field, electric displacement, the voltage, the capacitance, and the energy. So I'll start quickly by looking at just the setup and kind of drawing in the electric fields, drawing in the vectors, so that we can analyze them as we go through the problem. Initially, because we have the positive charge Q up here, negative charge down here, we're going to have an electric field between the plates. We'll call this E1. And it'll point from positive to negative, as all electric fields do. When we slide the dielectric in between the plates, of course we're going to induce some polarization as the negative charge in the dielectric gets more attracted to the positive charge on the upper plate, and the positive charge in the dielectric moves down towards the negative charge on the parallel plate. And of course this will give us kind of a setup like this, where we see a polarization in the dielectric material itself. Now we still have this external field E1 between the parallel plates. Because we have the battery disconnected, what that means is that essentially the charge on our plates is going to stay the same, which is one of the questions, but I'll kind of say that here just for the explanation of the diagram. This electric field will stay the same. We'll end up with some electric field component within the dielectric material itself, a contribution. We'll call that E2. And then we have a total field still between the two of them, E total. We'll have a potential difference between the two plates here, and we'll have a charge on the top plate and a charge on the bottom plate. Of course, the electric displacement for a linear dielectric is going to be in the direction of the electric field, D. So for part A, the question asks, what happens to the magnitude of the electric field of this parallel plate capacitor with a dielectric in between? Does it go up, does it go down, or does it stay the same? What we see is that we initially have the field going down between the positive plate and the negative plate, and that's the field E1. And when we have this dielectric material in between the two plates, we're going to have a polarization that induces a different electric field, a response field, E2, which points opposite to E1. And again, this is because the positive charge moves down in the dielectric, the negative charge moves up, so we have this response field moving from positive to negative E2. Now our total magnetic field, E total, is simply the sum of E1 minus E2, because E2 points opposite to E1. Now of course, because E2 is greater than 0, that means that the total magnitude of the electric field is going to be less, so it's going to go down, then less than E1. E total is less than E1, which was the initial magnetic electric field between the two plates. That's part A. Part B asks what happens to the electric displacement D. So initially we had some electric displacement in between these two parallel plates like so, and we recall that the electric displacement depends on the amount of free charge in the system. Here we have the free charge on the top plate and the free charge on the bottom plate, and when we slide the dielectric inside of the two parallel plates, the free charge that's on the top and the bottom, because we're disconnected from the battery, doesn't change. And what that means is because the electric displacement is dependent on the amount of free charge, the electric displacement will stay the same. It will not change, even with this dielectric in between the material, in between the two plates. So again, that comes from the fact that the electric displacement depends on the amount of free charge in the system. The free charge is the charge on the plates in this case. We're disconnected from the battery. So what that means is that even when we slide that dielectric inside, the amount of charge on each plate will remain the same. So the total free charge is the same, therefore the electric displacement is the same. So this will be the same. Question C says, what is the change in the electric potential V? So delta V will go up, down, or stay the same. So because we know that the total electric field E total, which is the sum of E1 and E2, will go down. I guess I should put a magnitude over these just to keep the vector and scalars quantities equal. But the delta V is proportional to the electric field, as of course our integral of E dot dl with the negative sign out front, that's the proportionality. So because the total magnitude of our electric field went down, that means that delta V will also go down, so it'll be lower. That's part C. Part D asks us for what happens to the capacitance between these two parallel plates. So because we know that the capacitance is the total charge over the change in potential delta V, this is a formula from your textbook, we have that the Q, again, because we disconnected the battery, the Q on each plate will remain the same, but the delta V goes down, which means that our C will go up, or will increase. Because delta V is smaller, which means that this division divided by a smaller number means C will increase. We also can say that because, if I continue this over here, we can also say that capacitance is equal to epsilon over epsilon naught times the vacuum capacitance, which is just the relative permittivity times CVac. And because this is always greater than 0, because epsilon is always greater than epsilon naught, this means that C will also go up. That's just another way to think about it. Finally, for part E, we want to know what happens to the energy. And now the energy, we have two different ways of looking at it. We can say that it's equal, W is the energy, it's 1/2 C times delta V squared. We can also say that the energy is 1/2 Q squared over C, if we simply plug this formula in. In both cases, we're going to notice that C will go up, but delta V will go down, and delta V goes down squared. So that means that the delta V term will contribute more to this multiplication here, this product, which means that in this case, the energy will go down. And also, if we see in this case, we have that Q, the charge stays the same because we're disconnected from the battery. Our capacitance goes up, we're dividing by a greater number, so here the energy will also go down. So we can conclude that the energy between the two parallel plates goes down. And that's part E. So to summarize A through E, and kind of look at our diagram setup one more time, and talk about what happens in each value we're looking for here. We again have that our parallel plates are set up so that we have some sort of potential difference V naught between them. We have positive charge on the upper plate, a negative charge on the lower plate, and an electric field between them. When we slide that dielectric in between, we're going to polarize that dielectric. So there's a bound positive charge on the bottom, a bound negative charge on the top. This induces a response field within the dielectric material, going from positive to negative. Excuse me. And this response field will counter the initial electric field, and we'll have a total electric field that is smaller. So that part answers part A, where we have the magnitude of the electric field will decrease, it will go down. Because we have that the charges on the plate stay the same because we're disconnected from the battery, so even though we slide this dielectric material inside, the charge on each plate will remain the same because the battery will not work to keep that potential difference the same. So the free charge on the plates, the same, because the electric displacement depends on those free charges, the electric displacement will remain the same. We look at question C, which asks what happens to the potential difference between the two plates. In this case, we have the battery driving it to a constant V naught. In this case, the charges on the plates remains the same, so delta V should stay the same. However, because we have that dielectric material in between, the electric field created by those plates is decreased, which means that because the potential depends on the electric field due to this integral, because the magnitude of E is smaller, the magnitude of the potential difference is also smaller, it will go down. In part D, we have that the capacitance is equal to the charge on the plates divided by the potential difference between the plates. Q remains the same because we're disconnected from the battery. Delta V goes down, so this difference here, this quotient, is that delta V on the denominator is smaller, so our capacitance is larger and it will go up. We can also see that due to the permittivities and the fact that epsilon is greater than epsilon naught, and when we slide that dielectric material in between, the epsilon factor will increase. Finally, when we're looking at the energy, we have two different ways of looking at it. We can look at the capacitance and the potential difference, which we know that the capacitance will go up, however the potential difference goes down, and we have that going down squared, so that term dominates, and we have the total energy decreasing. Or we can look at it in terms of the charge and the capacitance, and the charge we know that stays the same on the two plates, positive and negative remains the same because we're disconnected from the batteries. The capacitance will go up, which means that we're dividing by a greater number, and the total energy will go down. So in this case, it's very similar to that worksheet where we know that we slid the dielectric in between, and it depends on whether or not we're still hooked up to that battery. So if we're hooked up to the battery, the charges will move so that we have that maintained potential difference, which is a completely different problem, but also fair game, and might be something you want to look at, kind of the difference between this problem when we disconnect the battery and a different problem when we remain connected to that battery. That might be something interesting to kind of understand the difference between the two. That also helps kind of understand how the electric displacement works, what happens to the polarization in the material, how the capacitance changes. Those are all really good points to look for the final. This is a very theoretical question, but it's a completely fair game because there's formulas that are involved and you have to remember what these formulas mean. However, all of the conceptual stuff is really important and pretty much encapsulates all of chapter 4. So I think this is a really good problem to understand for the final. And of course, if you're able to look at that worksheet and see what happens when you slide that dielectric in between, then everything should be pretty straightforward.